Hello students, let us continue module 5. In this video, let us discuss about intermediate code generation. That is a phase of the compiler, which is also called as intermediary between front end and back end of the compiler. As we already studied, there are different phases of compiler. They are lexical analysis, syntax analysis, semantic analysis, then intermediate code generation, code optimization and all. This intermediate code generation lies in between semantic analysis as well as code optimization. Let us discuss in detail. Uh, Here in this chapter, I will discuss about variants of syntax trees and tree address code. We have already discussed about syntax directory definitions, then evaluation order, application of SDT in the previous video. So, how to construct syntax tree as well as one more variation of syntax tree, that is called as DAG, directed acyclic graph, as well as another intermediate representation, tree address code. Let us discuss in this video. So now let me tell you something about intermediate code generation. So it is the interface between front end and back end in a compiler, as I told you earlier. So ideally what happens is the detail of the source language are confined to the front end and detail of the target machines are confined to the back end. So here we will study the intermediate representation. I mean different types of intermediate representation and intermediate code generation. Now observe this figure carefully. You have intermediate code generation over here. So before this particular intermediate code, you have parser and static checker. That means this parser also includes lexical analyzer as well as syntax analyzer. The static checker means semantic analysis. So after these three phases, your source language statement is given as input for this intermediate code. So intermediate code can be written by using any language like C or C++, which is left to the programmer or the designer of the compiler. So after this step, the output of this intermediate code is given as input for directly code generator, or you can have one more phase called as code optimizer in between. So the entire thing, that is starting from lexical analysis to a part of intermediate code generator, it is called as front end of the compiler, and last two phases, optimization and code generation, is called as back end of the compiler. Some other points related to intermediate code generation. There are different types of IR. Mainly we will discuss about syntax tree and tree address code. So this syntax tree, which is related to the source program. So let us call this syntax tree as high level intermediate representation. And coming to this tree address code, which is nearer to your target code or the machine code, so it is called as low level intermediate representation. So a choice of intermediate representation is left to the programmer or compiler designer as well, because it varies from compiler to compiler. Okay, so programmer may think of syntax tree, or they may think of tree address code. So IR may be actual programming language or the data structure shared by phases of the compiler. So we can use any programming language or any data structure to implement intermediate representation. So for example, let us go for C language. The reason behind this is it is flexible and compiles into efficient machine code as well as widely available. So people are more popular about this C language, as well as it is flexible to use. Now, one type of syntax tree, that is called as DAG. DAG means directed acyclic graph. So what is this DAG? How to construct DAG for the given expression? What are the differences between syntax tree and DAG? We will discuss in detail. Students, please consider this as very important topic. You may get easy questions under this topic like construct syntax tree, DAG for the given expression and all. It is scoreable also. Try to understand the concept and try to solve the problems. So it is sometimes beneficial to create a DAG instead of tree of expression. So how to construct this, let us study. Here the main advantage of directed acyclic graph is it will identify the common sub expression and then use the knowledge during code generation. What do you mean by common sub expression? Let me explain with this example. Consider A plus A star B minus C plus B minus C into D. Here you can see A twice, B twice, C twice and D once. So in this example, A is common, B is common as well as C is common. So this is our syntax tree as we discussed in the previous chapter. What is syntax tree? It is nothing but a tree which has root node as operator and leaf node as operands. So how this can be written? You always try to construct syntax tree from bottom to top like this. So first consider parenthesized expression b minus c. So I wrote this part first. That is first write minus, then b, then c. Okay. And one more parenthesis expression b minus c exists. No? So minus, then b, then c. After completing this part, then go for remaining expression. What is remaining expression? Here you have a star b minus c and here b minus c star d. So complete this part. So I took this star operator here. For this star, one operand is a. See here, a is one operand, b minus c is another operand. So for this star, one operand is A, another operand is this minus. So this part is completed now. Similarly, complete this part. B minus C already completed. So star I took. Left operand is minus, that is B minus C as you see here. Then right hand side D. Okay, now this part is completed. What next? One addition is here, another one addition is here. So since addition takes from left to right, so associativity is from left to right, first this addition takes place. So plus, for this plus, one operand is a, another operand is this star. Have you observed? So I wrote a left hand side and another operand is this star. That completes this part. So what is remaining? Only this plus is remaining. So I took plus. For this plus, one more plus. This plus is one operand. A plus A star B minus C. That is one operand. Another operand is B minus C star D. That is this star. So this completes my syntax tree. Now, how to construct this DAG? Okay, so it is very easy if you understood the construction of syntax tree. As I told, DAG always identifies common sub-expressions. So, how many times you have A's or B's or C's in the given expression, DAG contains only one occurrence like this. A only once, B only once, C only once and D only once. So first consider B minus C, okay, as like syntax tree case, minus B and C are the operands. Okay, when this part is completed, then go for A star B minus C. So for star, A is one operand, this minus is another operand. Okay. Then what happens? This B minus C star D you have to complete. B minus C, okay, put star operator here. For this star, B minus C is one operand and this D is another operand. Okay, after completing this part, then what to do? One addition here, one addition here is remaining. So for this plus, put plus over here. Then which is the operand? Operand is A. This A is this A is already wrote once. So just put a curved line like this. For this plus, A is one operand and star is another operand. See, for this plus, A is one operand, star is another operand. No need to write A second time. So just put a line like this. Okay, this part is over. Then last plus part, addition part is remaining. So write plus, which is the operand. Another, this plus is one operand. So our line is like this. And this star is another operand, like this. So this is about construction of DAG. I think you have understood how to construct a DAG. So in the next slide, let us see some examples. Draw syntax tree and DAG for A plus A minus B, A plus A minus B. Some simple example. A is equal to A plus B, A plus B plus A plus B, and this expression is for you. I will try to show the solution for these four, and then after observing these four example, you try to write syntax tree and DAG for this expression. First one, listen carefully. A plus A minus B. Okay, so here this column syntax tree and this column is DAG. A plus A. So first consider parenthesis expression. So plus, then one operand is A, another operand is A. Twice you have to represent in syntax tree. Then minus of B. So minus is here. For minus, this plus is one operand, B is another operand. Then how to construct a DAG? Only once you should write A, isn't it? Since it is a DAG, it identifies common expression. So only once, only one occurrence of A. So I wrote A here. That is the operand for plus, correct no? A plus A. So just put curved line for A like this. Minus B as usual, write minus, and one operand is plus, another operand is B. So how you can read this one? A plus A minus B, that is DAG. Then second example, A plus A minus B. How to do? First consider parenthesis expression. So this part I completed first. Then for plus, one operand is A, another is minus. Coming to DAG, A minus B, this part is easy. Then A plus, so plus is here. A is already I wrote, so just curved line I will use like this. How to read? A plus A minus B. A is equal to A plus B. Third example, syntax tree, A plus B. Then it is assigned to A. So for assignment operator, one operand is A, another operand is plus. Coming to DAG, A plus B part is over. Exactly similar to our this previous case. Instead of plus, we have minus. That's it. Last example, A plus B, A plus B. Correct? So, as it is syntax tree, I wrote A plus B part here and A plus B part here. Then for this plus, this is the root node now. For this plus, one operand is this left hand side plus, another operand is right hand side plus. So draw a line like this, that is syntax tree. Now coming about DAG. Only A and B are the operands. So only once you should write A and B. Okay. So A and B, for plus, this A and this B operand. For this plus, once again A and B are the operands. It is fine if you write like this because A plus B or B plus A, they are same. Correct no? So you can read this one like B plus A. Nothing, no problem will happen. Okay. So A plus root two nodes plus and plus which exist over here. Okay. Then for first plus, this plus is one operand, this plus is another operand. This is about construction of syntax tree and drag. Students, please try this example. Now, one more thing. Here in this slide you can observe there are two methods to construct a DAG. Now we have seen how to construct a DAG manually. Okay, now what is the implementation idea behind this? There are two ideas. One is using STD. What is STD? Syntax directed definition, as we discussed in the previous chapter, and another one is using value number method. Let me explain one by one. STD for creating tags. What you have to do? First, consider the grammar like this. Let us go for simple desktop calculator grammar, that is addition and subtraction. E gives E1 plus T, E gives E1 minus T. Okay, E gives T, T gives E, or T gives ID or number. Suppose this is the grammar, then semantic rules we can write like this with the help of our construction of syntax tree like node and leaf. When we require node and when we require leaf, remember node is required for an operator followed by two operands, and a leaf node is required for constructing leaf nodes. Suppose leaf nodes are identifier or numbers, you can create a new leaf node like this. Leaf, it is the label ID. I will name it as ID, and actual value is ID dot entry. Entry means symbol table entry. So number means number. It's the name of the leaf, or label for the operand, and it is actual value. Similarly, how will you create a node? New object node, then label is plus, operands are E1 and T, E1 dot node and T dot node. Okay, similarly it follows for the minus E1 dot node and T dot node. So first consider the production, then semantic rules. So this is the STD. Using this STD, how we can create DAG? So as you know, DAG identifies common sub-expression. So once an object is created, its reference is used. We are not going to create another object for the previous identified sub-expression. Consider the same example which we have discussed, a plus a star b minus c plus b minus c star d. So first what happens? So P1 means object 1. Object 1 is equal to, first consider this a, leaf node with id comma entry for a. Okay, following consider this a, leaf node is created like this. Let us call it as P1. Then another operand is a itself. So whenever this particular method tries to create an object like P2 is equal to leaf node id entry for a. At that time it identifies common thing, so the returned object is P1 only. It is not P2. Clear, no? Because A is the common thing. Then we require B. So leaf node with the entry B is created. Object is called as P3. Okay. After that we require C. So leaf node with the entry C is also created. Now parenthesis expression B minus C. So what to do? A node is created with the operand operator minus and operands P3 and P4. Why it is P3 and P4? Because the objects for B and C are now called as P3 and P4. Understood? P5 is the object, new object which is created for this B minus C with the help of label minus followed by P3 and P4. So B minus C is stored in P5. After B minus C, we have to compute A star B minus C. So create a node with the star P1 and P5. Why P1? Because A is P1. So P1 and P5. So A star B minus C is stored in P6. So after that what to do? This particular part we will finish now. So A plus. So node, create a node with the plus P1 and P6. P1 and P6. So P7 means A plus A star B minus C. So first half is completed. Second half B minus C into D. So uh, the method tries to create a leaf object for B, but it is nothing but P3. Then for C, it is nothing but P4. Object returned will be P3 and P4 only because they are already there. Then what is next step? B minus C. So once again node with the minus and P3 and P4, but that B minus C is already stored in P5, right? No, P5. So see here node minus P3 P4 and node minus P3 P4 same. So P5 will be returned. What next? Entry for D has to be created. That is leaf node. Leaf node with the ID entry of D. So D is created. Then this star B minus C star D object P12 is created. At the end, this plus addition with the node label plus P7 and P12. What is P7? P7 is addition of P1 and P6. That is A plus A star B minus C. And P12 is B minus C star D. So P13 is this one. So these are the steps to create DAG using STD. So if the question is asked like this, explain construction of DAG with the help of syntax directed definition, you need to write this production followed by semantic rules followed by creation of object like this, which is followed by DAG diagram like this. For our example, this is the DAG. Since I have already discussed DAG over here, I didn't put a snapshot for this particular step. Understood? No? STD. What is the method for creating DAG using STD? Production, semantic rules, then object creation followed by the DAG diagram. This is the one method of creating DAG. Another method is called as value number method for constructing DAG. Okay. Consider the simple example expression I is equal to I plus 10. See, I occurrence of I is twice, but we have to use only once. How will you write? First consider I plus 10. So for plus operand, first operand is I, second operand is 10. For this is equal to, draw a curved line like this. I is equal to I plus 10. This is the DAG. This DAG can be constructed with the value number method. Now there is an algorithm to construct DAG by using this method. This table is also important. What does it say, this algorithm? First search the array for a node M with the label of left child L and right child R. Okay, so what happens is, if it is a leaf node like this, okay, listen carefully. If there is a leaf node like identifier or number, a table is created like this. So first column, name of the operand, that is identifier, and next column to entry for I. Suppose this is an identifier, we have to write like this, to entry for I. Suppose this is the number, the given number should be written, that is 10. Okay. Then suppose it is operator like this, okay, plus, then we have left child and right child. Okay, left child and right child. So left child means left operand, right child means right operand. Now start searching the value number array for left child and right child. Plus, and one more thing, here it is represented like this: index, this is 1, second is 2, sorry, 1, 2, plus is 3, then equal is 4, like that. Now for plus, left child is id, no, id, and right child is a number. So consider this value now. plus 1 2. Plus is the operator and 1 is the index of ID and 2 is the index of number. So left child is 1 and right child is 2. Okay, then plus is remaining. Sorry, equal to is remaining. So equal, for equal, what are the operands? One operand is I. So left child is 1. 1 means this ID, entry ID. And right child is 3. 3 means this plus. Have you observed? 1, 2, 3. 1 is ID, 2 is num, 3 is plus. So for is equal to left child is 1 and right child is 3. So this is the index table for this particular DAG. Now observe the algorithm again. First step, search the array for a nodium with the label of left child and right child. If there is such a node, return the value number. That's why I told you, return the number, index number 1, 2, 3 like that. For plus, ID is already there. Its number is 1. For number 10, ID entry is already there with the number 2. So 1 and 2 are returned. If not, create in the array a new node n with the label of left child and right child with its return value. Suppose you have this I plus 10 once again in the expression, then direct use this index 1, 2, 3. No, you can use this index 3 in the place of I plus 10. We may also use a hash table for better searching. This is the value number method. Now coming to 3 address code. Let me explain this 3 address code in the next video.